We are going to take a look at the Kleene-Brouwer order. If you already know what the lexicographic order is, then this is quite easy. It's the same thing as the lexicographic order, except for how it handles prefixes. So it exactly flips the ordering of prefixes. If that didn't mean anything to you, that's fine. I think to learn about the Kleene-Brouwer order, it makes sense to look at the lexicographic one at the same time, because that one's quite intuitive. I mean, what both of these things do is that they take a set that is ordered, an order, and the Kleene-Brouwer order, or the lexicographic order, both of them are then going to be an order on the words that you can make with this set. Or rather, the finite sequences. This is my notation for finite sequences. So if I have an alphabet, if X is an alphabet, A is smaller than B is smaller than C, the usual order, then X smaller omega is going to be equipped with an order as well, either the Kleene-Brouwer order or the lexicographic order, or any other order, but we're going to look at these two. And what is inside this set is all the words that you can make with these letters, or the finite words, or the finite sequences. So it could be the word ABC, it could be the word cab, it could be the word A, or it could be the empty word that I'm going to write like that. So that's what we're getting. So the Kleene-Brouwer order and the lexicographic order describe this order relation right here. And I'm going to, denote this one KB, denote this one L, but sometimes I might forget it, and then you better just understand from context what it means. So the lexicographic order does this in the same way that is done in a dictionary. So a dictionary orders words alphabetically, and what does that mean? It means that if we have two words like cab and cat, it looks for the first point where these two words differ, in this case at the third position, and compares those two symbols. So since we know that B is smaller than T, we then know that cab is smaller than cat. So this works in both. This is how it's done in both the Kleene-Brouwer order and the lexicographic order. There is a special situation that happens when one word is a strict prefix of the other. For instance, I could have cab and I could have cabbage. So now we're wondering how these two are related, because obviously this method doesn't work. There is no point that fits in the length of the shorter word where the letters are going to differ. And so we need to think of how to handle this case. And the lexicographic order does it in the way that we are used to from dictionaries, which is that the shorter word, the prefix, is going to be smaller. So cab is smaller than cabbage. And the Kleene-Brouwer order does it exactly opposite. So cab is actually greater than cabbage. This means that the Kleene-Brouwer order has a greatest element, the empty word, and the lexicographic order has a least element, which is the empty word. But even more things will be true, as we will see. All right. I like I think there's a nice way to think of this as well, if you don't want to have these two separate rules. We can also think of it as, well, both of them have this rule, except that with the Kleene-Brouwer order, before you compare two words, you actually fill them out. So any two words, whether it's cab, cat, or cabbage, before I compare them, I actually fill them up with a new symbol, with infinitely many new symbols. And I do the same in the lexicographic order, except I'm going to take another symbol to infinity. So I turn them into infinite sequences, except that in the lexicographic order, I place this symbol below A. It's going to be the smallest one. And of course, this generalizes to any X. It doesn't have to be ABC. And for the Kleene-Brouwer order, I place this above all the other letters. Yeah, and then once I've done that, all I need is this rule. And I don't have to think about the prefix case anymore. What's the point of the Kleene-Brouwer order? Well, where I encountered it, which was in a book about reverse mathematics, it was important that the Kleene-Brouwer order sort of handled well-foundedness between X and the finite sequences in X in a nice way, in a way that the lexicographic order doesn't. And that's what sort of made it nice to work with. To understand that, let's think about how these things generalize. So if we just have the finite words, there is an even more intuitive way to order these words by simply taking the empty word, then taking A, B, C, and so on. It could be infinitely many if we want, depending on what X is. Perhaps it might be nice to start writing the integers instead of letters, because when I see letters, I feel like it's going to be finite. And then everything that has 1 as a prefix is going to be below 1. So here I'm going to have 1, 2, and 1, 1, 1, of course, and so on. And the same thing here and here and here. So at any point in this tree that I made, it's an upside down tree. At some point, I would have the encoding of cab, which would be, confused myself. This would be above cabbage that I'm not going to write out, but it's going to be above this one. Or if this was much longer, then anything that is the prefix, if one word is the prefix of another, then that word is going to be above the longer word in the tree. So this is a very natural way that you can order any set, except that this, of course, is a poset. It's a partial order. Not any two elements are comparable. 1 and 2, for instance, are not comparable. And what both the lexicographic order and the Kleene-Brouwer order do is that, given such a tree, they give us some way of turning this partial order into a linear order. So we can order the elements in this tree along a single line. Whatever sort of order type that line may have, it's still going to be a single line. What the lexicographic order does is, it goes to, now we also have this property. So knowing that X is also ordered, we can now go to the smallest element and then first sort everything below 1 and write that in a list. Then we can sort everything below 2 and also write that in a list. Everything below 3, and so on. And then within one, we did the same thing, right? So yeah, this is going to be quite a high order type, but that doesn't matter. So this is what the lexicographic order does. And the Kleene-Brouwer order is a bit hard to imagine because it does the reverse. It's harder to imagine. It goes to the bottom, it starts from the bottom, it goes all the way to 1. And then it starts from the bottom again, and it goes all the way to 2. And within this, it does the same thing. I hope I said that right. If I said it the wrong way around, let me know. So once we are looking at the Kleene-Brouwer order in this way, we can express the following theorem, which is that if a tree is well-founded, any tree, honestly, we don't even have to start with X now. Now we can just think of a tree. It doesn't really matter what it looks like, it's just any tree. If a tree is well-founded, then so is its Kleene-Brouwer order. I wrote well-ordered here, but it doesn't really matter. That's not the point here. It's well-ordered anyway. The interesting bit is that it's well-founded. What we actually mean by this, or what this means, in case you don't know what well-founded means, this is not quite what well-founded means, but it's what is usually meant when we write it here. And it is classically, it's kind of the same. We mean that if a tree has an infinite chain, or path, I think it's called, if and only if the Kleene-Brouwer order has an infinite descending chain. So an infinite path in the tree is of course a path where we start here, or we start anywhere, and we can descend infinitely far. The Kleene-Brouwer ordering having an infinite descending chain, so any linear order having an infinite descending chain just means we have, x1 smaller than x2, x2 is smaller than x1, and so on, infinitely far, with no equality at any point. So yeah, it sort of preserves well-foundedness, and this is an if and only if statement. I'm not going to prove this, but it's quite fun to prove. If a tree has an infinite descending chain, then you can immediately see that same chain is going to be infinitely descending in the Kleene-Brouwer order. So if I can have a path going on like this, it's going down and down and down and down. And this, I'm claiming that this same path is going to be an infinite descending path, an infinite descending chain in the Kleene-Brouwer order. Why? Because before we said that prefixes, so something like AAA is going to be smaller than AA in the Kleene-Brouwer order. We were thinking of it as, well, this is longer. But now that we're looking at trees, we're thinking of it, well, this is a prefix of this. So prefixes are always greater. And by prefix, in the tree case, because now we're just starting with any tree, T is any tree that is a subset of this. Now we're starting with any tree, so by prefix we just mean something that is above it. So if we are descending along a chain, then by the Kleene-Brouwer order, for instance, let's just take this. Well, no, let's not take an example, let's do it properly. We have this, and then below it in the tree we have x2, and then below it in the tree we have x3, and so on. Then by definition of the Kleene-Brouwer order, x1 is greater than x2 because it is a prefix of x2, and so on. And the tree doesn't contain duplicates, so now we've got an infinite descending chain. So this is this direction of this theorem, or the other direction of this theorem. case you care about this formulation. Yeah, that's pretty much what I wanted to talk about. I mean, notice that the lexicographic order does not have this property. In fact, you know, if we just look at 1, 1, 1, 1, 1, 1, and so on, so a special infinite descending path. This is an infinite descending chain in the tree, but it is not an infinite descending chain in the lexicographic order, because actually this is greater. So in L, this is an infinite growing chain. Well, that's a bit confusing because my ones look like the greater thans, but oh well. Whereas in the Kleene-Brouwer, it's exactly flipped. Yeah, so actually the Kleene-Brouwer is sort of preserving the order of the tree right here. Alright, that's what I wanted to talk about. If you want to find this theorem and just generally see what role the Kleene-Brouwer order can play, I was reading the book about reverse mathematics. Actually, let me just show it to you. By Mamet and Defarov. So it might be flipped right there. But that's alright, you can pause and figure it out. Yeah, let me know if you have any questions, and goodbye.